In this video, we're going to explain the final idea of this chapter, which is the mechanical energy. The mechanical energy of a system is the sum of the system's kinetic and potential energies. This is its formula. The mechanical energy is the sum of the kinetic energy of a system plus its potential energy. In the application, consider a cart that slides on a certain track. The cart's mass is 50 kilograms. The gravitational field strength is 10 meters per second square. The cart leaves point A with negligible speed. It descends to reach point B with a speed of 14 meters per second, then ascends a height of 4.8 meters until it reaches point C with a speed of 10 meters per second. The height of point A relative to the gravitational potential energy reference is 9.8 meters. It is required to find the mechanical energy of the system C, Earth, at points A, B, and C. The mechanical energy at A is the kinetic energy at A plus the gravitational potential energy at A. The cart leaves A without speed, so its kinetic energy at A is 0. And since A is above the reference level, we write plus mgha, which is equal to 50 times 10 times 9.8. The result is 4,900 joules. The mechanical energy at A is 4,900 joules. Note that the mechanical energy at A is only the gravitational potential energy. Since the kinetic energy at A is 0, the mechanical energy at A is purely the gravitational potential. Now to find the mechanical energy at B. It is the kinetic energy at B plus the gravitational potential energy at B. The kinetic energy at B is half mvb squared plus B is on the reference level of the gravitational potential energy. So the gravitational potential energy at B is 0. Half times 50 times 14 squared. The mechanical energy at B is equal to 4,900 joules. Note that the mechanical energy at B is purely kinetic, since the gravitational potential energy at B is 0. So the mechanical energy at B is purely kinetic. Now for the mechanical energy at C. It is equal to the kinetic energy at C plus the gravitational potential energy at C. Half mvc squared plus. Point C is above the reference level of the gravitational potential energy. Then the gravitational potential energy at C is plus mghc equals half times 50 times 10 squared plus 50 times the height of point C, which is 4.8 meters. The result is 4,900 joules. What can we conclude here? The mechanical energy at different points is equal to 4,900 joules. We said that the mechanical energy of the system C, Earth, is conserved. At A, the mechanical energy is purely gravitational potential. At B, the mechanical energy is purely kinetic. So when the mechanical energy is conserved, the gravitational potential energy is totally transformed into kinetic energy. During its descent, the cart's speed increases, its gravitational potential energy decreases, while its kinetic energy increases, because the mechanical energy is conserved. We say that the decrease in the gravitational potential energy is transformed into an increase in the kinetic energy. A frequent question is asked: what happens to the mechanical energy when the cart is subjected to a force of friction from A to B? If the cart is subjected to a force of friction from A to B, friction will produce heat or thermal energy. This thermal energy is lost by the system to its surrounding. So where does this thermal energy come from? It comes from the motion of the cart, since the motion of the cart is opposite to friction. And as a result, the thermal energy leaving the system comes from the motion of the cart, or specifically, the mechanical energy of the system. A part of the mechanical energy is transformed into thermal energy, and as a result, the mechanical energy will no longer be conserved. In this application, friction was assumed to be negligible. The car moved freely, hence the mechanical energy of the system was conserved. In the presence of friction, the mechanical energy is no longer conserved. Part of it will transform into heat. In the case where the system moves freely and without friction, the mechanical energy of the system is conserved. If friction exists, the variation in the mechanical energy is equal to the work of the force of friction. Let's solve an application. A solid S leaves point A of an inclined plane without initial velocity. It descends on the plane until it reaches point B. The inclined plane makes an angle of 30 degrees with the horizontal. The horizontal plane passing through B is taken as a reference level for the gravitational potential energy. The mass of the solid is 100 grams. The gravitational field strength is 10 meters per second squared. The length of AB is 160 centimeters. Part 1. Calculate the mechanical energy of the system at A. The mechanical energy at A is equal to the kinetic energy at A plus the gravitational potential energy at A. The solid leaves A from rest, so its kinetic energy at A is 0. And A is above the reference level. Then the gravitational potential energy at A is plus mg HA. HA is the height of point A from the reference level. This is the height HA. Now consider the right triangle AHB. In this triangle, sine 30 degrees equals to the opposite side, which is HA, over the hypotenuse, which is AB. Then HA equals to AB sine 30. AB is 160 centimeters divided by 100. So 1.6 times 1/2, this is 0.8 meters. Now the mass is 100 grams, which is 0.1 kilograms times 10 times 0.8. The answer is 0.8 joules, which is the value of the mechanical energy of the system S Earth at point A. In part 2, calculate the speed at B if friction is neglected. Calculate the speed of S at B if friction is neglected. Now we know that S is moving freely from A to B. In the absence of friction, the mechanical energy of the system is conserved. The mechanical energy of the system S Earth is conserved. Since S moves freely and without friction. S is left without speed from point A and is left to slide freely and without friction. The mechanical energy of the system is conserved. Then the mechanical energy at B is equal to the mechanical energy at A, which is equal to 0.8 joules. To determine the speed at B, what is the mechanical energy at B? It is equal to the kinetic energy at B plus the gravitational potential energy at B. The kinetic energy at B is half mvb squared plus B is on the reference level, so the gravitational potential energy at B is 0. As a result, the mechanical energy at B is half mvb squared. Then the speed at B is radical 2 times the mechanical energy over the mass. Radical 2 times 0.8 over 0.1. The speed is 4 meters per second. Let's add a third part to the question. In the presence of friction, the speed at B is 3 meters per second. This is the speed at B. Let's call it Vb prime in the presence of friction. Now, in the absence of friction, the speed had a value of 4 meters per second. In the presence of friction, S reaches B with a lower speed than in the absence of friction. In part A, calculate the mechanical energy of the system S Earth at B. The mechanical energy at B is equal to the kinetic energy at B plus the gravitational potential energy at B equals half mvb prime squared plus B is on the reference level, so the gravitational potential energy at B is 0. Half times 0.1 times 3 squared. This is equal to 0.45 joules. Part B. Deduce the work of the force of friction. Note that S moves freely from point A to point B. The mechanical energy is 0.8 at A, and the mechanical energy at B is 0.45. There is a decrease in the mechanical energy. This decrease is transformed into a work of friction. We write the work of the force of friction is equal to the variation in the mechanical energy from A to B, of course. This is equal to the mechanical energy at B minus the mechanical energy at A. 0.45 minus 0.8. The result is minus 0.35 joules. This is the work of the force of friction. Part C. Calculate the magnitude of the force of friction assumed constant. The work of a constant force of friction from A to B is equal to F times AB times cosine of the angle between F and AB, where AB is the displacement. Note that the force of friction acts opposite to the body's motion. The displacement is in this direction. Friction acts opposite to the displacement. The angle between the displacement and friction is 180 degrees. F times 1.6 times minus 1. And the work of the friction is minus 0.35. Then F is equal to minus 0.35 over minus 1.6. The answer is 0.218 newtons.